Hello and welcome back to Calculus 1 section 3.6 on derivatives as rates of change. So we are going to apply derivatives now. We are going to have what you would call the real life situation because calculus is fake, right? We're going to take a look at, again, average and instantaneous, mention those, and then go to other areas of application as well. But let's start first with the notion that the average rate of change is your good old calculus concept, which you either had as f of b minus f of a divided by b minus a. You can also do this as f of x plus age minus f of x divided by age. So either one of these two. And that was your average rate of change. So that's your algebra, right? And then we have the instantaneous rate of change. Oops. Which was the derivative, which was f prime of x is equal to that limit age goes to 0 of f of x plus age minus f of x divided by age. So we talked about the difference between these two using velocity earlier, where we said that if you cover the distance 0 to 10 miles in, let's say, 10 minutes, you were driving 60 miles per hour on average. So now what does that mean? Well, that's your average speed. So average speed was 10 miles minus 0 miles. So this is your end. This is your start. Divided by, now 10 minutes is 1/6 of an hour minus 0. Miles, there we go, miles per hour. When I take 10 minutes is equal to 1/6 of an hour. So we get 10 divided by 1/6, which is 60 miles per hour. This over here is average speed. Average speed. Now, what that number means is that since you know you started with the car having 0 miles per hour and you got to your destination 10 miles later, 10 minutes later, and you parked the car, you know that those two speeds are 0 and you had to speed into whatever speed you were driving and then slow down. But your speed was constantly changing and you were driving at some places faster than 60 miles per hour, and at some places if you had to stop with a stop sign or a red light or something like that, maybe you had to slow down because you were stuck behind someone, right? Go under the speed limit and so on. Those times were all below the average speed, and then you had to drive faster than the average speed to kind of make up for the times when you were driving at the slower speed, so they can all together average at 60 miles per hour in this case. Now, instantaneous velocity measures the speed of the moment you are in, the moment when you are measuring, that infinitely small age goes to 0 moment. So if you take a look at it, it's like literally like a taking photograph of the speedometer, and you say at second, at 3 minutes and 57 seconds, I was driving 54 miles per hour, right? So you have that map, right? When you got in the car, turned the car on, And that's when the timer starts ticking, 1 second, 2 seconds, 3 seconds, 4 seconds, right, going on all the way to the 10 minutes. So you start the car, the timer starts, and then you push the gas pedal, which changes the speed from 0 to whatever other number. Now, depending on the car, you will reach some speed faster or slower. That doesn't matter. What matters is that your speed was changed. And you could have looked at the speedometer and say, in 1 second, I was doing 35 miles per hour. In 2 seconds, I was doing 50 miles per hour. In 3 seconds, I was doing 65 miles per hour. So it took you 3 seconds, let's say, to accelerate 0 to 60. Let's say. I mean, usually it's not the case, but let's say. So it takes time to get to these, but if you are to look at a particular time, right, you have the speed of that instant, and that's what the derivative shows. So now, what we can have here is something that we would call the position function. Let's say s of t, and that position function is a function that will tell you how far you went, right, given a certain time. So it takes you, I don't know, in 3 seconds, you will be, 200 feet away, let's say, in 3 seconds. So we have the position function, and then we have the velocity function. Which is the derivative of position function, so ds dt. And you can quickly see that if your position, which is how far you go from your origin point where you started your journey, that's measured in miles. And now you have it divided by time. That's miles per hour. And that's your good old miles per hour, which is the speed. Now, velocity and speed are not the same concept. Speed is a part of velocity. Velocity is actually a vector which has the direction in which you will go, and it also has the length of that vector would be the speed, which is how fast you are going. Because you can go in whatever direction you pick, but you can go slow, you can go fast, right? So you get to pick the velocity, and that's just the speed. Like you get to pick how fast you're going, but when you take that and a direction in which you are going, you get the concept of velocity, which is actually a vector. Now, much more of that, obviously, in physics and calculus 3. Right now, we're just doing plain vanilla, right, one-dimensional motion. And then we have acceleration function at the end, which is acceleration time, which is change of velocity. And it's also the second derivative of position. And that one would be, if we use miles per hour squared, because you can see that there is a square on t. There is no square on s. That's why it's miles. But there is a square on t, so that's time is squared. So we have now something very important to understand here. When you see this notation ds dt, you will read that change in s over change in t. So this d is read as change in, and it's actually the derivative, and the notation we are using is because we are still actually working on the old formula, but now we have the limit in front to make the denominator as small as possible, right? Denominator going to 0. So the notations are, for the average, you can say change in s divided by change in time, and for the instantaneous, which is your derivative, the velocity in time is the first derivative of s in time, which is ds dt. So you see the two notations, and this triangle here is actually delta. That's the capital D in Greek alphabet, which is very similar to my native Cyrillic alphabet. For us, capital D looks like this, and for Greeks looks like that. So, and the lowercase delta for both of us. I mean, no, for us is like this, but doesn't matter. So when you look at the Greek alphabet, right, you have seen delta before. You have seen, now you see capital delta. Capital delta means change. And that simply means the subtraction of the two values. So S1 or S2 minus S1 divided by T2 minus T1, where over here, for the derivative, we know we have to use that limit. So now, how do we use this? Well, if I say that I want to take a look at the projectile motion, so I fire something from whatever, 5 feet over here, I toss a ball, I toss a rock, right? We fire a human out a cannon from that circus act or whatever. You can calculate, if you know what the weight is of that person and you know how that cannon works, you can always predict where that person is going to land. Those things are calculated. It's not like someone just volunteered to get into that cannon until they figure out where the net should be, right? So overshoot the net by 30 feet, smash it in concrete or something like that. No, the person would stand on the scale, say, okay, this is how heavy the person is, this is the angle of the cannon, blah blah blah, initial velocity, all of those things, and they can actually figure out exactly where that person is going to land. So let's put something soft over there, right? Otherwise we have to get the new person every time we do this, right, in a circus. So now when you take a look at the equation like this, in physics they tell you that the s distance or the y distance, we can use y, let's use s, whatever. I'll call this later on s0. So s of t, because it's in time, s and t is -1/2 gt squared plus v0t plus s0. So this is an equation that you get in your physics class, and we are going to actually derive this equation for the first time in Calculus 2 fully, but then you will have a whole bunch of lectures in differential equations later on what you can do with these things. Develop terminal velocity, develop escape velocity, whole bunch of other stuff, impact velocity. You can just develop a lot of things if you take differential equations course. But now let's say this equation is given, and if I want to figure out the velocity, right, well, I know that I need to take the derivative of the s function. Now 2 goes down and kills the half, so we just have negative gt plus derivative of t is 1, so it's just v0, and s is a constant, derivative is 0. So we have our equation for velocity. And you can take one more derivative, which is acceleration. And when you take a look at your equation here, derivative of t is 1, so we just get negative g. And you see that acceleration is equal to the negative gravity, meaning acceleration downwards. If you throw a rock up, right, the rock will come down because acceleration is towards the center of the larger object. Now, if you want to, be so smug and say, well, yeah, Earth is the biggest object here, so everything goes there. Yeah, think about it a little bit, because there is a sun as well, and then the Earth has to bend its way around the sun, because sun is way more massive with a much larger gravitational pull. than the Earth. So the so you know, it's always what the larger object is and how much larger object is, so they can work out. Now, gravity is very weak, obviously, as a force. So any smaller objects, right, we can easily lift. I mean, we have been evolving around here for, you know, millions of years. So clearly we are well adjusted to the gravitational pull of the Earth, which is the acceleration downwards. So we have seen the acceleration. When you throw something up, it's going to go down with this negative g acceleration. Now, all of these formulas are given in physics with slightly different notation, I guess. This one could be written as velocity final is equal to velocity initial plus acceleration times time, and acceleration that could be negative g if you need it to be, right? So you might have seen it that way. You might have seen it velocity final minus velocity initial is equal to at. That was another form, same equation, just another form of writing it. Some people use capital F and a zero there. It's just there is a lot of different ways to write, but they all mean the same thing, right? So the final velocity, which is the velocity you're measuring that you want to know, minus initial velocity, which is the velocity you gave to the object when you throw it. That's the difference between throwing and dropping the object. The initial velocity, the v0 part in our original equation. You can get rid of this stuff from physics and just focus here on this term and say initial velocity is what we give to the object as we throw it. When you drop something, right, you make the oops. Well, that object that you drop from your hand is going obviously to fall on the floor, but that one does not have any initial velocity. When you drop something, it just goes straight down and it hits the floor. So v0 in that case is 0 because there is no initial velocity. But if you want to toss something to go any further in any direction, you have to give it some propulsion. So you have to throw it, or you have to strap a rocket on it and propel it, right? So in this case, right, if you want to have a rocket going against the gravity, which is where escape velocity comes in later on, as I said, for calculations. If you want to do the rocket launch, or you want to toss a rock, there is no difference in terms of physics. There is absolutely no difference because both of those are projectile motion, and both of those are subject to this equation here. Now, if you take a look at the equation, what are the important aspects? Well, clearly, how hard you throw and from which height you throw, right? So basketball players should be as tall as possible. Volleyball players should be as tall as possible because they have nets and hoops and things that are high up. So obviously, if you are taller with the same initial vector, right, the ball or whatever the object of the game is, it's not that it's just going to go higher; it's also going to go further. So that's another thing. Now soccer, well, short people are okay, right? Because they're also going to have a shorter center of mass. It's going to be easier for them to turn suddenly and so on because they need to do all of those things, right? So, you know, kind of sport will dictate that. So you have the height from which you throw the rock or a ball is important, and it's also important on how fast you throw, right? Is it a small or a large throw? And now also it depends on which planet you are doing that on, right? Is it Earth? Is it Mars? Is it, you know, where? Because gravitational pull is different on every planet. If we had people evolving parallel to us on Mars, yeah, them showing up on the Earth, you can knock out every single one of them with a basic flick, right? Break every bone in their body with a little flick, because their bone density would be much lower than ours and so on, because they don't have to fight the gravity so big as the gravity of the Earth. Mars is smaller than the Earth, therefore has a smaller gravitational pull. Therefore, you do not have to be as strong and tall as on Earth. So, you know, when someone says, what if Martians existed and then came to conquer us? Well, just flick them. That's all you need to do. Flick them, literally. You don't even have to use weapons or anything like that. Just flick. That's enough. Moon would be even more pathetic than that, right? Because that's just non-existent in terms of, right? Well, it's not non-existent, but in terms of the gravitational pull. So these are the equations, and now you go into a problem, and the problem tells you, here is the equation for this parabolic motion. What is how far did the object go after 3 seconds, let's say, and how fast is it going? And we know the acceleration. Obviously, acceleration is always g because we are doing the free fall, but we can calculate the position, and we can calculate the what else we can calculate? We can calculate position, which is s, and we can calculate velocity on how fast this thing is moving. So if you take a look, I'm just going to jump into homework. Obviously, example that is in the book you can read and enjoy. If we go to the book and just pick literally any of these problems. Here, I'll do problem 20. That's the last problem of this bunch. So they tell you that f of t is given as negative 6t cubed plus, this is no longer a parabolic motion, plus 36t squared minus 54t, and 0t4. So everything is happening within 4 seconds. Find the velocity function, graph the velocity function, what is happening with the object, okay, and then we have determined the velocity and acceleration of the object at t equals 1. So they are looking for velocity at 1 and acceleration at 1. That's what they're looking for. Determine the acceleration of the object when the velocity is 0. So how much is acceleration when velocity is 0? So that's another good question. All right, so let's take a look at this. We said in order for us to solve the velocity problems and so on, we just have to take derivatives. So velocity function in this case was going to be negative 18t squared plus 72t minus 54. So that's our velocity function. And now we can calculate acceleration function by simply taking one more derivative, which is negative 36t plus 72. So these are my formulas. And now what we see is that we do not have constant acceleration. This is not a free fall problem. In a free fall, the only acceleration that is present is acceleration due to gravity between the object and the mass of the planet. And we perceive that the object is going down because the planet is way more massive than any object you can possibly think of tossing up or down, obviously. So the object will always go down and the acceleration will always be negative g. However, in this particular example, we differentiated twice and we came up with the acceleration function which has a t in it, which means it's dependent on time. Now, this is like you driving a car. Car has the engine inside, right? And when you push the gas pedal, the car goes faster. Your acceleration is faster. Now, your acceleration is not always straight, right? It's not always the same at the same magnitude. Sometimes you push the gas pedal more. Sometimes you push the gas pedal less, right? So it accelerates at different rates. So if you know that if you want to go um, to a speed at a slower pace, you don't have to push the pedal as much as if you want to go somewhere quickly, you floor it, right? So in this case, now we have the functions, and they want us to figure out how much is the velocity after 1 second or 1 minute, whatever the units are. So in this case, you just plug in 1 everywhere, which will technically just give you this calculation. And we end up that the velocity is 0, if I calculated this correctly. So that's going to be negative 72. Yeah. So velocity is 0. And then we calculate acceleration at 1. And that is going to be negative 36 plus 72, which is 36. Now, if I give these units, then we can call velocity meters per second and acceleration meters per second squared. You can also do feet per second and then feet per second squared. You can do miles per hour, right? And this would be miles per hour squared, which is something that you don't use when you talk, everyday talk. But miles per hour you pretty much use all the time. And if you go anywhere else in the world, right, it's going to be kilometers per hour, the way they like to write it, which is kilometers per hour squared.
So, Professor, how is it? So why is gravity negative 9.8 meters per second squared?
It is due to the size of the planet and the curvature of the planet. So it can be actually calculated if you measure the curvature. So it's due to the size of the planet. The size of the planet, the mass of the planet dictates the gravitational acceleration. So the smaller the planet, the smaller the number. Larger the planet, larger the number.
But why is it squared? There.
Oh, because you have the time, right? So when you have your position S, right? S is measured in, let's say, meters. Well, let's do feet. So S is measured in feet. That's the position. Then when you take the derivative of that in respect to time, right? You get your units. Again, you have S on top, that's your feet, and you have your time over here on the bottom, and that's going to be, let's say, second. And that's going to be your velocity. Now, when you take one more derivative, that's going to be the second derivative. And here, as you see, that the top still has feet because it's a single S. But the denominator has S squared because it's T squared, and the measurement for time is seconds. So seconds squared. So the units are position, velocity, acceleration, and the units are feet per second squared. The more derivatives you take, the exponent in the denominator keeps rising. So those are the rules of the units. So we have our velocity, let's say 0 per meter per second, and then acceleration would be 36 meter per second squared. Now, again, you're only going to have one of these pairs per problem, depending on which units the problem used. And if they use different units, let's say they use feet and hours, we don't do feet per hour, right? The snail might be doing feet per hour, but we don't. We do either feet per second or mile per hour. So you would have to convert something to get either into feet per second scenario or the mile per hour scenario. But at no time you're going to go and say, oh, it's, blah, blah, feet per hour, because no one does that. So there are these pairs that are set up for us technically. So meter per second and feet per second, they are comparable. And then you have mile per hour and kilometer per hour. And then it just depends whether you are talking, right, imperial units, which are the ones in the middle, or you are talking the metric system international units, which is given in meters and kilograms. So that's it, guys. That's the acceleration and velocity. These are the three equations where this one is given to you and you are supposed to just differentiate to come up with the other equations. And now, once you have those equations, you can calculate, at 1 second or 2 seconds or 10 minutes, right? You can calculate how fast the object is moving. You can calculate how fast it's accelerating. If you get the negative number, then it's going to decelerate, right? Slow it down, and so on. So it all depends on what kind of a function you get up there. And this function, no one said that this function has to be a polynomial. Could be e to the t, could be e to the negative t, could be e to the negative 5t, could be cosine, could be sine, could be literally anything, because you should know how to take derivatives of whatever function is provided. Now, most of these functions over here that I see in the book, they're all polynomials, which is kind of lame. But you can get into any other function if that function satisfies the conditions. Let's talk more about the rate of change. Another aspect of rate of change, we can talk about population. I don't care if you want to talk about humans or rabbits. You want to take a look at the rate at which population grows, the rate at which population diminishes, and so on. Way more about all of this, obviously, in differential equations, which is the course that is actually the most important course for all of these sciences you will ever do, because all of the formulas are from there. But now, without going into differential equations and understanding change from their perspective, what we want to learn here is the change once the formula is given to us. So if I tell you that the population formula for whatever is 500 units, e to the, let's say, 0.03 t, I have some kind of a growth model, because k is bigger than 0. Positive k, in our case 0.03, means that this population is growing over time. Now, it's a particularly bad model, obviously, because as you can sense, this model will start at 500 units, and because it's exponential growth, it will go like that in time. And we know that the planets cannot sustain infinite population of anything because we have finite surface area. You can start there. The other part is also finite resources and everything like that. So population change is measured, again, by the derivative. I can calculate average population change, which would be population at time 2 minus population at time 1 divided by T2 minus T1. That's the average population change. But we can also compute instantaneous population. So instantaneous population change by figuring out the derivative of T. And that one is simply as 500 times 0.03 e to the 0.03 t, and then you multiply this to get the population is 5 times 3 is 15 e 0.03 t. These two zeros will be knocked off by the decimal, and you're just left with 5 times 3. You don't need a calculator for something like that. So now I have my population model, which measures the change in instantaneous change in population. So now I can say, what is the change in year 3? Change in population in year 3. Well, I'm looking for P prime of 3, and that's very simple. 15 e 0.03 times 3. You punch all of this into the abacus, and let's see what we get. So that's going to be 15 times e raised to 0.09. That's give me 16.4. Now we are not going to have a 0.4 of a unit. I don't care if you're talking about rabbits or human babies. You should not be having 0.4 there. So you can claim that we added 16 units of whatever, 16 units to our population. So that's what we added. 16 units to our population in a year 3. You want to round it up to 17, right? Because I could also accept 17, even though properly mathematically, right, to round this would be down to 16. But you know what? If this person is on a way 0.4 of a time, right, we can count it in. So this is the difference of the average population. The average population is going to give you the average change for all years. Year 0, year 1, year 2, and year 3. So it will take all of the changes and average them all together to give you the average change. But the instantaneous one, the derivative, it only gives you the growth in population in that one particular year. So I'm just going to say whatever ridiculous numbers. Let's say year 2 ended with, I don't know, I'm just going to say 519 units. And then year 3 starts with 519 units. And then year 3 ends with plus 16, 535 units, right? So this is what it means. So you just see that in this year, between the start of the year and end of the year, in that one year, you added extra 16 units or 17, whatever way you want to round it. And that's what instantaneous means. The same thing for the velocity, right? If you get pulled over for doing 80 on 65, you cannot have the excuse that 15 minutes ago you were driving 65, because you were not clocked when you were driving 65. You were clocked when you were doing 80, and you are pulled because you were doing 80 that instant when you were clocked. It doesn't matter that 15 minutes ago you were doing 65. It doesn't matter that an hour ago you were parked, not having any speed. None of that matters, right? But all of those speeds will be computed in the average speed. When you were parked at zero, when you were zero at the red light, when you were zero at the stop sign, when you were accelerating after the stop sign or decelerating to get to the stop sign and stop, right? All of those speeds, all of those different speeds are mushed together in the average for this one answer at the end, where when you are clocked by the radar and the cop says you were doing 80 on 65, that means the instant you were clocked, you were doing 80. And the fact that you were doing 65, 5 minutes ago, that doesn't have anything to do, because that instant is a different instant. So now, if you're thinking about the population, we can go and we can say we doubled the population of Earth in the last 50 years, right? I think 1970s to 2020, we doubled the population of humans on the planet. So that we added uh, 3.8 billion people in these 50 years. Guys, 50 years is only 2 generations of people, right? The parents and their kids.
Hey,
Usually, right, parents would have their kids when they're, let's say, they're in 30s. They used to have them in teens, then they pushed it for 20s, and now they usually have them in 30s. So this is only 2 generations, and we doubled the amount in those 2 generations. So you see that when you look at this, right, number, you understand that the average goes through all of the 50 years. But we can go and we can calculate how many people we added in a just year 2020. And that's something interesting, to understand, especially when you're talking about this COVID nonsense. The population in United States with a 200,000 dead, right? If that's the number, or I don't care, take 250,000 dead, whatever the number is. If you take that and you take a look at what's the added population for the 2020, right? You will see that we are not even breaking even, right? But again, you have to do these calculations in terms of the amount of people the population brought up. So instantaneous calculation will tell you the amount of people added, right? So that was the 16 units. Now, obviously, that's going to be much larger for United States, which is the third largest country in the world in population, right? You have China, then you have India, and then United States is the third largest population. So, of course, that the large population is going to have a large number of COVID deaths, because that's just common sense. Because applying the same percentage that it's everywhere in the world, when you apply that percentage on the large number, you are going to get a large number. When you apply 0.06% to a country that has 7 million people, you are going to get numbers in hundreds. So that all makes sense to people that understand mathematics on a very basic level, right? People who have IQ more than 12. Now, it's not a talking point at all. It shouldn't be the talking point, but it is talking point because people can do basic mathematics. So now, looking at these calculations here, the population change is very simply computed by taking the derivative, and then when you have the model, you can just compute per year, right, how many people you add to the population in 1 year. Now, usually I assign those problems for the projects and things, so people can have fun with the research and say, okay, this is the model that we use, which we will learn in pre-calculus, right? The P equals P0, e to the kt. You get the two points in time. Let's say you take 1970 and the population in that year, and you take, I don't know, 2000 and the population in that year, and then you can come up with a model because you will calculate P0 and you will calculate K using those two. Once you have that, let's say you want to do it for US, right? This information is available on Google, and then you use basic pre-calculus 1 to compute the model, something that would look like this. Once you have this, you take the derivative and you see, right, for 2020, how many people you are adding to the population in 2020. And then you keep going like that. Now, obviously, that's all crude calculations because this model is bad. We do not use this model. We use logistics model. So you have to go to differential equations to learn that model where there is a cap on how many people you can have around. And when you go over that cap, well, there's no farmable land, there is no energy, there is not enough for everyone. And that line will be also mentioned in your Calc 2 and then differential equations. It will be carrying capacity of the planet, which is the maximum amount of people that the planet can sustain to have enough farmable land and enough farmable, land for space, like to bring up the, to make the housing and everything else. Any questions, concerns? Because we are done with the population and the change in population.
Hey, Professor, if you're adding more people on the planet, like, doesn't the mass of the planet go up?
All insignificant, because the planet is on the order of 10 to the 27. So you cannot add as many people. Plus, everything, when you have the person grow, the person develops cells, which is all atoms and molecules which came from food, from nutrition. So it doesn't actually, it only recycles. So we are not adding the matter to the, by having more people, more animals, we are not adding actual matter onto the planet, because it is the food and nutrients from the food that get built into and developed into a person, right? And then the excess is, right, pooped out. So the thing is that you have the mass of the planet doesn't change at all. And what I wanted to say first was, even if that was the case, that you are creating matter from nowhere, still the size of the planet, the mass of the planet is so much bigger than the population that it's crawling on its surface, that it's really insignificant in terms of the people. But that's a really cool thing to wonder about. So yeah, but yeah, you grow in size from being an infant into a full-grown person. And I know you're taller than me, man. um, so you grow into a full-grown person by actually eating the nutrients that were still right in um, form of plants and animals, right? So that's what we eat and that's what we have. Okay, we have to talk about one more concept here in terms of now economics and business, and this is going to be cost analysis for the cost analysis for business, where we're going to take a look at the cost analysis for a particular business where they are developing whatever they're making, some units. And we want to take a look if the business model is good, right? Now, this is one of the rare examples where I'm actually going to take the problem that it's done in the book and go over it. I think this is actually the first instance in Calc 1 that I do that. And I always announce that I actually did exact problem that they did in the book. Usually I don't like to do that, but this problem is so damn good that I just can't pass on it. So Cost analysis. So what we are going to do now is we're going to take a look at the cost analysis of the business. The cost is a very important thing to consider when you're running the business, because when your costs high, your profits are down, and the business has to fold, obviously. And a lot of stuff goes into a cost. Um, the salary, right, of workers is a cost, right, because that has to be written off from the revenue, which is how much money is collected for selling the goods. So the cost of the salary. Then you have all of the other costs, which is creating machines, buying machines, installing, maintaining machines, buying and maintaining trucks to transport the goods from you to the consumer. So if you are running business, and that's very, very difficult, a lot of businesses, over 90% to 99% of businesses that start fail. Only specific people can ever run a business, um, because they have to be very smart in this cost analysis and make some really tough decisions to have the business stay competitive and stay afloat. So the profit is when you have revenue minus the cost, and you have to always have the cost because you have raw materials, you have workers, you have research and development, right, engineers. So you have, or research labs to make medication. So no matter what your business is, even if it's baking, right, there is always cost, because even if you run baking business, you still have to buy flour and salt and cookie dough and stuff like that, right, to make your product. So it doesn't really matter what you make, you always have cost. And the cost is always divided into the cost per unit, in terms of the fixed cost, right, and the cost per unit. Now, fixed cost is stuff that you know buy once and you just have it, right? You know that your workers are going to cost you this much every month. You know that the machine that you purchased for $3 million is $3 million spent, and there is the machine, right? Use it. The truck you purchased for $60,000, there you go. You have your truck. It's right there, right? And then you have the cost per unit produced. That's the variable cost, because to make something, you have to buy raw materials. So if you make something out of plastic, you have to buy raw materials for plastic, or metal, or wood, or flour for baking. It doesn't matter, but the more stuff you make, the more raw material you have to buy. Now, obviously, the more raw material, the bigger the cost of buying that material. So to make a cost function, right? Cost function, you hire a mathematician to go in and figure out what are all of the accountants and so on. You hire people that know mathematics. I don't care what you're gonna call them, mathematicians, accountants, wizards, whatever. You hire them, and they come up with a cost function which contains that variable cost plus the fixed cost. And as I said, fixed cost, you rented or bought the building, machine, truck, salaries for workers, right? You hired people. That's all your fixed cost, doesn't change per month. And then variable cost, that's the cost on how many units you want to produce. So are you making hundreds of something, or thousand, or a million of something? Obviously, if you're making thousand, those, let's say, dry erase markers, you're going to use less plastic than if you make million of them, right? The fact is that the machine that makes them could cost $1 million, let's say. So you're not going to buy a machine for $1 million and make 100 markers and shut down the factory, right? You're going to make millions of those markers and send them all over the world. So the trick is that we want to now analyze the average cost to make something, and what they call marginal cost, which is the derivative. So we have the average cost. This is now our part of our calculus lecture, which is C with the bar on top. And that's the cost divided by how many units you made. Number of units produced. And then the marginal cost is just good old the derivative of the cost function. That's all it is, just a derivative. And as I said, I simply love the example in the book because it really shows the dynamics of why this analysis is so damn important, especially if you are, guys, business major, economics, and so on. This is example for you. And then go and look into other stuff as well. All right, so what is the function? So someone is going to say for the business gives you the cost function, cost function as C of x equals negative 0.02x squared plus 50x plus 100 for the units 0 to 1,000. That's it. And we know that we can quickly calculate the formula for average cost because all I need to do is to divide each one of these terms by x. So negative 0.02x plus 50 plus 100 over x. And then the marginal cost would be another formula, which is the C prime, and that's just the basic derivative. So negative 0.04x plus 50. Now, when you take the derivative here, it's a basic polynomial. So taking the derivative, that 2 will drop down and multiply, 2 into 0.04, and then derivative of 50x is just 50, derivative of 100 is 0. And now we want to take a look at the cost analysis if we make 100 units. Again, I don't care what you're making. Shoes, you're making computer keyboards, cars, it really doesn't matter. What I want to know now is my cost per item produced going down? Because if it's going down, I'm in good shape. If the cost per item produced is going up, oh, we're going to have a problem with this business because the cost is eventually going to be so large that the business will have to fold. So you have to have a business model that you can sustain, right? The cost needs to go down. Let's go and see this. The average cost of making 100 units is what? Well, plug in 100 in there. So that's negative 0.02 times 100 plus 50 plus 100 over 100. That gives me negative 2 plus 50 plus 1 for the total of, this is going to be $49 per unit. Cost, right? So if I am to make 100 units with the cost function, now remember, cost function had the fixed cost and had the variable cost over here. Variable cost has these variables per unit, right? Made. And the fixed cost is machines and whatever, salaries and everything else. So it seems that if I want to make 100 units, each unit on average costs me $49 to make it. All right, that's a very important information to know because I better set up the price to sell this higher than 49. Because if I set it at 49, I am breaking even. My business is not turning profits. And if you are not turning profits, well, guess what? There is no research and development to improve your product. Every business needs to have a profit so that they can keep developing their product. If the business is not making profit, then it will eventually be overtaken by other companies, and they lose. You see what AMD did with Intel. They absolutely demolished them. I mean, if you're not following that, like, Intel is done. They have to reconfigure, reimagine everything they have, because AMD absolutely destroyed them on all fronts. They lost everything. They lost servers, they lost single computing, they lost hyper-threading. It was always AMD's, right? They lost the small processor market for cell phones and tablets. They lost the entire market because they did not develop the 10 years that Intel was the name, right? 10 years. They did not do any serious research and development. They stayed at the processors they had. When these guys came up, they absolutely destroyed them on all fronts, right? If you are running Intel processor in your computer now or buying one, you are just buying the underdog that you can't even believe. Now, and paying premium price. So now let's take a look at the marginal cost for this business. So now I know that I need to set my price much higher than 49 bucks so that I actually turn profit if I'm making only 100 units of my product. How about C prime of 100? That's going to be negative 0.04 times 100 plus 50, and this is going to be negative 4 plus 50, which gives me the marginal cost of $46. Now, it's not $46 per unit. It is $46 for the 100th unit. Now, this is a little bit harder to understand, but if you are to make only one unit and then just close the factory, that's a very expensive one unit you made. Think about it. You had to buy, let's say, a $3 million machine, and you use that machine to make one thing. You bought the machine, you bought the installation for the machine, maintenance for the machine, you bought the worker to operate the machine, you have a team of engineers to develop the thing that goes into machine and make it, right? That's an insane amount of cost. Let's say altogether at the end cost you $5 million. And you produce one dry erase marker. Well, congratulations, you just produced a $5 million marker, because it cost you $5 million to make that one unit, right? If you make the second one, oh, now $5 million, so each one can be 2.5 million, roughly, right? The thing is that the more units you make, you have less cost to produce that last unit. So you can see that on average, it costs $49 to produce one unit of whatever you're making, but the 100th unit, right, that came on that conveyor belt, so you made units from 1 to 100, the 100th unit, the last unit that you have on that conveyor belt, was $46 in cost to make it, where the first one was much higher, 50, right, 56, that's 52. Anyway, now, we will see this and understand it even better when we do our cost analysis for 900 units produced. So what's the average cost for 900 units? Negative 0.02 times 900 plus 50 plus 100 over 900. This is equal to negative 18 plus 50 plus 11 cents, right? Who cares? So the total over here, is that 11 cents? 100 divided, 1 divided by 9? Yeah, 11 cents, good. So this is going to be 32 and 11 cents per unit. Ooh, all of a sudden, we see that if we make more units, the average cost goes down. Now, that should be common sense. Just using the story I told you earlier, if you only made one marker, it costs you $5 million. If you made two markers, then each one is 2.5 million. If you made 5 markers, each marker is $1 million. So now you see that the more you produce, the average cost of production goes down. Why? Well, because the workers are still working, the salary is paid for a month. Maybe they need only 3 days to make 100 units, right? And then waste 2 days of doing nothing. But maybe you have a full week of work for 900 units. But let's say they do 100 units in a day, whatever. Now, your fixed cost, remember, you're not buying new machine to make another 800, so that the fixed cost remains the same pretty much. You need to, you have some maintenance and so on, but you can see that the cost of average cost per unit goes down. So if you now set your price, right, to sell this product at, let's say, $60, right, that's almost double what you have at 900 units produced. And I'll give you another example very quickly. Marginal cost at 900 units. This will calculate the cost to make 900th unit. 0.04 times 900 plus 50 is equal to, and then this is a negative 36, right? 9 times 4, 36, good. Plus 50 equals $14 cost for the 900th unit. What? Right? So it costs you only $14 to make the 900th unit. The more you produce, the cost to produce that is less. So now we can have those Costco deals, right? Not everything is cheaper in Costco, but usually, you go there and you can save on ketchup if you buy a bulk of 12. Now, do you eat all 12? I don't know, but generally, right? So looking at this is a good business model. The more I am producing, the cost of production is going down. Now you hopefully understand why Elon Musk is a god of business, why he's able to run 10 companies and all of them be successful, right? What did he do first? He first put out Model S for $90,000, $100,000 per car. Why? Because the cost to make those cars is insanely large. He just didn't reinvent the car industry. He had to make all of the new machines that never existed, open new factories, train people to build cars they never been built before. That's all insanely expensive. So going into completely new business with something that doesn't exist is insanely expensive. So he starts with the most expensive, knowing that the people who want to have, expensive, cool looking toys will buy into it. And they did. Now he can sell a Model 3 for measly $35K, 3 times cheaper than what his Model S was. And then promise the Cybertruck at $40K. That car is going to be better than anything was ever made on the planet when it comes out. Right? Indestructible, technically indestructible, at the cost that no other can compete with. Now, this is the business model. You understand the business model? Because when you make something, when you have a good business model and you make something with a small amount of units, the cost of production is high and the price is high. As soon as you're able to develop your factories and make more of them, then you ramp up production, the cost of making those units in the future goes down for the already paid off equipment, right? And you become very, very competitive on the market, because you can always drop the price even more. Now, I gave you the Intel versus AMD, where AMD is outperforming every platform of Intel, and in some cases is half price. Half price for, let's say, 5% better performance. That's insane, right? So that's something that that you can all think about, and then you can look at the Tesla pricing and understand that he started with the most expensive, like S and X. Model X is 140K in some cases, the one with those Falcon doors that open on the side, right? That's $140,000 car. And then he goes, Model E, 40K, 30K, 35K, right? And then promises the truck that beats them all in every aspect, right, at the low price as well. So now I hope you understand how calculus can be used to look at the prices, the cost, to set up the price for what you manufactured or make. You also understand, hopefully now, why art is so expensive. If you have an artist spend 3 to 4 months painting one painting, it's obviously going to be up for $10, $15, $30,000. It's only one made. It's not a serial production of 900 same paintings, so he can put it up for, $17, $17.99. If this person was sitting there 3 months and painting, and the same person was practicing the art of painting for 30 years prior to that, having that painting sell for 30K makes perfect sense. Because think about it, 3 months, 30K, that's 10K a month. All right, how much is 10K a month? Well, someone who makes 120,000 working in a company, which is engineering, within 15 years of employment, you can reach 120 if you're a real engineer. Obviously, if you don't know your engineering, you just pass the classes, then obviously you're not in that boat. But those who really focus only on applied problems, who focus on learning to know the craft, and not focus on grades and tests and nonsense, but focus on the knowledge so they can use it later to actually be useful in a company and make money, those are the ones that have over 100K very quickly. And I know quite a bit of students who were in my classes before that started at 80K, and now are pushing over 100 already, working 5-6 years in industries. Primarily computer science, obviously chemical engineering, those are the ones that pay the best. That's it. Any questions, concerns, anything you would like to add or subtract from this? I gotta get the crickets thing in. When I ask a question and then no one answers within like 10 seconds, I can just push the button and it goes. That would be funny. Anyone? I guess this was perfectly clear. Awesome. So you can also read about elasticity in the the verbal example. It was not example with calculations. The examples of this at work were Tesla as a car industry, talking about Intel versus AMD, talking about painting and having an artist make one painting, right, over a period of, let's say, 3 months or 6 months, whatever, and put it up for $30,000 would make sense, right? So I mean, if it's the top-notch experienced painter and so on. So yeah, that's not yeah. I'm not talking about the calculations, because you can take the derivative, right? They do have a couple of these examples in the book for homework that you can run through and try. Cost function problems 43 through 46, so 4 problems that work similar. Another cost function 29 through 32, and a whole bunch of other problems. So, you know, try your homework on this, and let me know next class if you have, or office hours, if you have more questions. So we're going to take a break, and when we come back, the most important lecture of chapter 3 by far, chain rule, one derivative technique that you will be using forever, right? So that's all going to be at 3.7 when we come back. So here we go, epic music.